For this video, instead of sharing technical knowledge, I'd like to share one of my dreams. And that dream is a convergence of two ideas that are really brilliant and coming together rapidly, but they may not cross paths unless we get the idea out. This is a brilliant mind behind the YouTube channel Node Dojo, and he has created a system using parametric design that grants flexibility to well-made mechanical geometries. So you have a branching of one well-designed component into an infinite number of outcomes. And this is the essence of using digital tools to create hardware. This is the dream that we've all wanted since software paved the way to show how one user can share and then enable users with less expertise to borrow that brilliant design and then apply it in a new space without having to reproduce all of the effort. This outcome makes use of the high value and engineering stability of off-the-shelf steel rods as an example. That's one of thousands, so that your mass-produced components can then be utilized and made into a valuable asset inside of a design. So we touch modularity, we touch parametric design, and we can easily, readily jump into the plugging in AI tools, because now we have our geometry and our user defining the goal, and the AI can perform something like iterative geometric changes to adjust the strength and minimize the mass. Lastly, it touches on design for manufacturing, because this guy behind Node Dojo created the design package to accommodate 3D printing. So he has constraints in here, and he has understood the tolerances that can be achieved with 3D printing, such that this geometry can be then set off into a digital manufacturing process. Digital in this case meaning that from that file, the post-processing and the manufacturing can be done just with the computer tools we have, without extra users planning for how the tooling will be made, etc. Then here we have another brilliant system that touches on open source. It touches on free distribution of design components, and customizability and modularity, so that the user can take these brilliant, well-made designs with tolerances and manufacturability already integrated, and they can customize it to meet a new need. If you could remember one thing from this video for the next 10 years, it would be that when AI gets involved in these things, it can help you design a solution, but it cannot decide what problem needs a solution. It can't decide what you want. You can find my video from 2016 when I did my master's thesis. The subject was the optimization of a multidisciplinary system that was a satellite. And every result, so this is preceding the implementation of AI, but the tools behind it are all about optimization. Mathematically optimizing something. This is what AI does. It's an optimization problem. And the only way to achieve success, even with the best tools today, is if the optimization is based on a problem statement that is properly defined. You only get what you want if you know very specifically what you want. And in a system like this, you input what you want comprehensively and digitally accurately with the parameters that you plug into the constraints. As we advance from single disciplinary designs, such as a plastic assembly, to a comprehensive multidisciplinary system, then optimization is still mathematically possible, and AI will accelerate that. But the defining of the goals, the targets, will become vastly more hard, and it's the burden, it is the new task of design engineers, is how do we decide what we want? Getting what we want will take iterations, just like software is a digital tool to create a design that has many iterations. We can iterate freely and rapidly and collaboratively. We will need to iterate on our mechanical designs. And so these two amazing concepts will have to come together. This one is modularity. So when you change your mind and you want to make an adjustment to the design, you can just change one module. And the capturing of the value of highly refined off-the-shelf components, so that when you make a change, now suddenly you still have a mass-produced, quality-controlled element, a component that you can bring into your design or swap or change the length to achieve that next iteration. At the time that this Gridfinity system is able to integrate off-the-shelf parts that are high value and well engineered, then it could start to look something like this, where we have borrowed the strength of a standard component when the plastic can't do the job. We've borrowed the simplicity of hardware that comes off the shelf affordably, and we've decided sometimes when we need a plastic compliant part, we can just purchase that because the value is so high, it's faster and more accurate than 3D printing. And then we gain access to the elements that are outside of our discipline of expertise, and we can borrow from standards that give us reliable performance. I can't 3D print a motor. I don't know how to design this circuit, but I can be the mechanical engineer who characterizes this. So then allowing for collaboration between the many disciplines and allowing for a digital and repeatable component that can serve many different kinds of goals, not just organizing the lab. This combining of disciplines was and still is the entire essence of the Scuttle project, where we make a space for experts of different disciplines to combine their brilliant ideas and have it modular and changeable to achieve any other kind of output. And so you see two inventions here that are really made of the exact same components. And when it comes to performing a specific function, we just use the very best solution on the market, whether it's our design or someone else's design. Ever since 2018, we've been creating a system which is, beyond my understanding, the most documented, the most accessible, and the most modular and open basic robotic platform from which designers can start and pivot, or learners can begin with just an understanding of, maybe they know software, but they can learn the other parts on a functional system. And the business was not created to sell 1 million robots and get rich. We'll leave that job to companies like iRobot. Just like the two YouTubers I showed you, the efforts behind these designs are driven by inspiration and a desire to improve an ecosystem. It was done without any exterior funding, and we've reached learners and made impacts around the entire world, but we still will need a ton of help, just like Linux could not be produced just by Linus Torvalds. We need all the collaborators to discover each other and share. And when the private companies make great components and they don't share, we don't care that they're driven by unhealthy profit-making antics, because we have smart engineers around the world that have the brains to still integrate and capture the value and show for you how you can create a minimal viable solution, just getting the component that you need.